Dear students, today we are going to discuss about the mechanism of nucleophilic aromatic substitution reactions, that is the mechanism of SN-AR reactions. So let us discuss about the mechanism of nucleophilic aromatic substitution reactions. Actually, aryl halides are relatively inert towards nucleophilic substitution reactions under ordinary conditions. But under drastic conditions like high temperature and pressure, they undergo nucleophilic substitution reaction. There are two different mechanisms possible for nucleophilic aromatic substitution reaction. One is bimolecular displacement mechanism or addition elimination mechanism. Other one is benzene mechanism or elimination addition mechanism. Second mechanism that we will discuss in your upcoming class. So here we are going to discuss about the first mechanism, that is bimolecular displacement mechanism or addition elimination mechanism. The bimolecular displacement mechanism is operative when relatively weaker nucleophiles or bases bring about substitution in active aryl halides containing electron withdrawing groups in positions ortho and or para positions with respect to the halogen atom. And also it is a two-step mechanism involving an addition elimination sequence. So in bimolecular displacement mechanism, we had to replace the halogen by another nucleophile. So consider this reaction, the reaction of 4-nitrochlorobenzene. This is the halogen. We have to replace this halogen by another nucleophile OH group. So in this case, there is another group, that is nitro group, that is present in the para position. So because of the presence of the nitro group, this ring becomes more active. That means becomes more active towards nucleophilic substitution reaction. That means electron withdrawing groups withdraw electron from the pi electron cloud of the ring. So this ring becomes more electron deficient. So there will be some electron deficient character, means somewhat positive character for this ring. So a nucleophile with negative charge can easily attack this ring. So by the presence of electron withdrawing group at ortho and para positions, the ring becomes more active towards nucleophilic substitution reaction. So if there are electron withdrawing groups that are present ortho and or para position, then the ring will become more active and the mechanism also will be bimolecular displacement mechanism. If there are electron withdrawing groups only, the mechanism will be bimolecular displacement mechanism. And the other case, if there is electron donating group that are present in the group, that are present in the aryl halide, then the mechanism will be the other one, that is the benzene mechanism or elimination or addition mechanism. And also if there is no any group, that means if there is no electron withdrawing group or any electron donating groups that are present in the aryl halide, that means simple aryl halide is there, then that time also benzene mechanism follows. So if there is electron withdrawing group that are present ortho and para positions, then the mechanism is bimolecular displacement mechanism. Then if there is electron donating group and if there is no group in the aryl halide, then that compound will follow benzene mechanism for nucleophilic substitution reaction. So there are two steps. First step is the addition step, then second step is the elimination step. That is why the name addition elimination mechanism. So let us discuss about the first step of the mechanism. Consider the attack of a nucleophile Nu- on para-nitrochlorobenzene. Here it is given that nucleophile attacks on the para-nitrochlorobenzene compound. So step 1 for this mechanism, step 1 is the addition of the nucleophile. So here the nucleophile adds on the compound. The nucleophile attacks the carbon bearing the halide ion to form a carbanion intermediate which is stabilized by resonance. That means when this nucleophile attacks on this compound, these pi electrons will shift to this carbon, so that this carbon will become positively charged and this carbon will become negatively charged. Onto the positively charged carbon, this nucleophile will attack. Then this positive charge will get neutralized by the negative charge of the nucleophile. So the attachment will be like this. Then this carbon will get a negative charge and a carbanion will form, which is stabilized by the resonance. So this electron pair will shift to this bond. There will be formation of pi bond. Then this electron pair will shift to this carbon. So there is the formation of a negative charge formation. Then this negative charge will shift to this bond. Then at the same time there will be shifting of this electron pair. So in this way there are different resonance structures possible for this carbanion, formed carbanion. So in this step the hybridization of the carbon changes from sp2 to sp3, whereby the aromaticity of the ring is destroyed. So before the displacement of the electrons, or we can say before the attack of the nucleophile, this carbon was sp2 hybridized, but now it becomes sp3. It became sp3 hybridized, this carbon. This carbon became sp3 hybridized. This step is slow, rate determining step in the process. It is bimolecular and of second order. This step is slow because in this step there is loss of aromaticity. Aromaticity is destroyed in this step because of the change of the sp2 hybridized carbon to sp3 hybridized carbon. So this step is very slow and at the same time it is bimolecular. Two molecules are involved in this step, nucleophile and the compound. So this is second order. That is why the name bimolecular mechanism. This carbanion is known as Meitner-Hamer complex. It can be isolated. This is known as Meitner-Hamer complex. This is the resonant hybrid structure for the carbanion. So this is the first step, formation of a carbanion. Next we can see the second step. Second step involves the elimination of the halide ion. The halide ion departs very rapidly from the carbanion, restoring aromaticity and yielding the product. So in the second step, the carbanion, from the carbanion, the halide ion departs. This is the carbanion formed in the first step. So from this carbanion, the halide ion departs with this electron. So because of the shifting of this electron pair, it regains its, or it restores its aromaticity. So forming the nucleophilically substituted compound. So these are the two steps that are involved in the nucleophile substitution reaction of aromatic halogen compounds. First step is the addition step, second step is the elimination step. And also it involves two molecules, nucleophile and the compound, aromatic halogen compound. So that is why the name bimolecular mechanism. Next, moving on to the supportive evidence for addition elimination mechanism of aromatic nucleophile substitution reactions. The intermediate carbanion formed in the first addition step has been detected spectroscopically in several cases, and it has also been possible to isolate it in rare cases. It is called a Meitner-Hamer complex. We know that there is the formation of a Meitner-Hamer complex. That carbanion is known as Meitner-Hamer complex, that is formed in the first step, that has been detected spectroscopically by using spectroscopical methods. it was detected in several cases, and also it was also isolated in rare cases. So one evidence for the addition elimination mechanism, the isolation and detection of Mesenheimer complex or carbanion, that is formed in the first step. Then the rate determining step of the bimolecular mechanism of an SNAR reaction does not involve the cleavage of the carbon halogen bond. So the rate of the reaction is determined not by the nature of the halogen but by the rate at which the nucleophile attacks the aromatic ring. So in the rate determining step, this is the rate determining step. This involves not any breaking of the carbon halogen bond. So the rate of the reaction is determined not by the nature of the halogen. That means if we vary the halogen, if we use chlorine, bromine or iodine, the rate will not change because the rate determining step does not involve the breaking of this bond, carbon halogen bond. But the rate of the reaction is determined by the rate at which the nucleophile attacks on the aromatic ring. That is the only factor. Then in fact the reactivities of aryl halides, bromides and iodides in SNAR reactions are not found to be much different. That means if we change the halogen, it will not affect the rate of the reaction. That means in the rate determining step there is no breaking of this carbon halogen bond. That is why if we vary the halogen, the rate will not affect, the rate will not change. This is further evidence for the bimolecular mechanism for SNAR reaction. So there are two main evidences for SNAR reactions. One is there is isolation and detection of Mesenheimer complex, detection by spectroscopical method, and it also can be isolated, that is the carbanion formed in the first step. Then another evidence for the addition elimination mechanism, that is there is no change in the rate of the reaction when we vary the halogen. That means by if we use bromine, chlorine or iodine, there is no change in the rate of the reaction. That is another evidence for the addition elimination mechanism. That means if we use a compound, an aryl halide compound with a nitro group, that follows the addition elimination mechanism. That was proved by these two factors. Next, let us see about the reactivity of discuss about the SNAR reactivity. What happens to SNAR reactivity? By the presence of more than one electron withdrawing group at ortho and para positions with regard to the halogen in an aryl halide, that we are going to see. That means if there are more than one halogen group that are present at ortho and para positions with respect to the halogen atom, then what will happen to the SNAR reactivity, aromatic nucleophile substitution reactivity? This enables the carbanion, that means the presence of electron withdrawing groups at ortho and para positions enables the carbanion formed from the nucleophilic attack to have more resonance structures and thereby get more stabilized. That means because of the presence of electron withdrawing group that are also involved in the resonance structures. Here you can see nitro group is also involved in the resonance structure formation. So that will stabilize the carbanion. So if there are groups that are present at ortho or para position, electron withdrawing groups that are present at ortho or para positions, they stabilize the carbanion that is formed in the first step by involving the resonance. So such a group at meta position cannot involve in such a delocalization and hence cannot bring about stabilization of the carbanion. So if there is any an electron withdrawing group at meta position, that cannot involve in such a delocalization and giving stability by resonance. So only the groups that are present at ortho and para position can contribute stability by resonance. But if there is electron withdrawing group at meta position, that cannot contribute to the stability. In addition to the minus M effect of such group, minus M effect means resonance effect, mesomeric effect of such groups. NO2 group is having a minus M effect. Present at minus M effect means they withdraw electrons from the ring towards it, that is minus M effect. Present at ortho and para position, dispersal of negative charge on the carbon of the carbanion can also result from the minus I effect that they show. So because of the minus I effect, there is the possibility of resonance. So in addition to minus M effect, in addition to minus M effect causes resonance. In addition to minus M effect, there is the possibility of minus I effect of nitro group. I effect means, plus I effect means electron releasing effect, minus I effect means electron withdrawing effect. There is one addition effect, that is minus I effect, that also causes the dispersal of negative charge. Negative charge is dispersed throughout the ring. Here you can see in this structure minus charge is here, in this structure minus charge is here, then minus charge is here in this structure. So my negative charge is dispersed throughout the ring by the minus I effect of this group. There is one addition effect, that is minus M effect. There are two effects, minus M effect and plus minus I effect. They together causes the stability of the carbanion. This obviously brings stability to the intermediate and thereby promotes reactivity. On the other hand, the presence of electron donating groups like OH, OCH3, NH2 at ortho and para positions with regard to the halogen in an aryl halide has an opposite effect. That means if there is electron donating group that are present at ortho and para positions, that can release electrons to the benzene ring. So it intensifies the electron density in the ring. So when a nucleophile attacks on the ring, there is high electron density. There will be high electron density. So it will repel each other. Because nucleophile is having negative charge, and because of the presence of electron donating groups, the ring is also having high negative charge. So they will repel each other. So nucleophile substitution will not occur. That means they tend to intensify the negative charge on the carbon of the intermediate carbanion in an SNAR reaction. At the same time, electron donating groups that are present at ortho and para positions will intensify the negative charge of the carbanion. That will also destabilize the carbanion. The presence of such groups thus tends to destabilize the carbanion, thereby decreasing the reactivity of aryl halide. So the presence of electron donating groups at ortho and para positions destabilize the carbanion and thereby decrease the reactivity of aryl halide, whereas the presence of electron withdrawing groups at ortho and para positions increase the reactivity of aryl halides, and also increasing the number of electron withdrawing groups that also affect the reactivity of the aryl halide. That means increasing the number of nitro group will causes increase in the number of resonance structures. So that is another factor for increasing the reactivity of aryl halides that we discussed here. That means if there are more than one electron withdrawing groups, that will increase the reactivity by increasing the resonance structures. Thank you.